Hey everyone, and welcome to The Explainer. Today we're talking about something invisible, something that's all around us, and something that works like our planet's very own giant invisible blanket. Yep, we're diving into greenhouse gases. They're absolutely essential for life as we know it, but it's all about a very, very delicate balance. So why the name greenhouse gas? Well, it's actually the perfect analogy. You know how a greenhouse lets sunlight stream in to warm up the plants, but the glass keeps that warmth from escaping? That's exactly what these gases do for our entire planet. They let the sun's energy in, but they trap some of the outgoing heat. It's a totally natural process, and a vital one, but the story gets interesting when we start talking about the enhancement of that effect. Okay, so let's break down how this actually works. It's kind of like a simple three-step dance. First, sunlight hits the Earth and warms up the surface. Easy enough. Second, the Earth, now all warmed up, tries to radiate that heat back out into space. But, and here's the crucial part, as that heat rises, our greenhouse gases are waiting. They catch it, they absorb it, and then they re-emit it, sending a lot of that warmth right back down, keeping our atmosphere nice and cozy. Right, so which gases are we actually talking about here? Let's meet the main characters in this whole atmospheric drama. While there are a bunch of them, there are a few heavy hitters that are responsible for most of the action. First up is the one everyone's heard of, carbon dioxide, or CO2. If these gases were athletes, CO2 would be the marathon runner. It's not the most powerful pound for pound, but its incredible endurance is what makes it such a critical player. And where does it all come from? Well, the big sources are burning fossil fuels, coal, oil, and gas for our energy in cars, plus things like industrial processes and deforestation. But the really key thing to remember about CO2 is its longevity. Once it's up there, a single molecule can hang around for hundreds, even thousands of years. That means its impact just keeps adding up, day after day, year after year. Okay, next in our lineup is methane, or CH4. Now, if CO2 is our marathon runner, methane is the powerful, explosive sprinter. It doesn't last long, but boy, does it pack a punch while it's here. Methane mainly comes from agriculture. We're talking livestock, like cows, but also from rotting garbage in landfills and leaks from natural gas pipelines. And here's the wild part. Even though it breaks down in the atmosphere in about a decade, over a 100-year timescale, it's more than 25 times better at trapping heat than CO2 is. It's a short, intense burst of warming. Now for a gas that kind of flies under the radar but is seriously potent, nitrous oxide, N2O. This one is another long-distance runner, and it's got some real power behind it. You'll find its main sources in modern farming, especially from nitrogen-based fertilizers, but also from burning fossil fuels and some industrial stuff. But check this out. Its significance is just staggering. Over a century, it's nearly 300 times more potent than CO2 at trapping heat. 300! And finally, let's talk about the synthetic supervillains of our story. These are the fluorinated gases. Unlike all the others we've mentioned, these guys don't exist in nature at all. They are 100% human-made. They're used in things like refrigerators and air conditioners, and aerosol cans, and for all sorts of industrial processes. Now, they're only present in tiny, tiny amounts compared to CO2, but their impact, it is completely outsized. Some of these gases are literally thousands of times more powerful than carbon dioxide.
So this brings up a really important question, right? We've got all these different gases and they all trap heat. But does that mean they're all created equal? Are they all doing it with the same strength? Well, the answer to that is a hard no. Not even close.
So to compare them, scientists came up with a handy metric called global warming potential, or GWP for short. The idea is actually pretty simple. It just measures how much heat a gas can trap over a 100-year period, and it uses carbon dioxide as the measuring stick. So CO2 is our baseline. It has a GWP of exactly 1. So how do the others stack up? Well, let's start with our sprinter, methane. Compared to CO2's baseline of 1, methane comes in with a GWP of about 28. That means, over that century, it's 28 times more powerful at trapping heat. But hold on, because we're just getting started. Nitrous oxide makes this huge leap, clocking in with a GWP of around 265. I mean, what a jump in potency, right? And then, even that number gets completely dwarfed by our synthetic supervillains. Just one of them, a gas called sulfur hexafluoride, or SF6, has a GWP that is just mind-boggling. It's 23,500. And this brings us to the really crucial point. You have to look at two things. Not just the power, the GWP, but also the lifespan. See, methane is powerful, but it's gone in about a decade. CO2 and nitrous oxide, though, they stick around for over a century. And then you have something like SF6, which is not only absurdly potent, but it stays in the atmosphere for over 3,000 years. Okay, so we've got all these different gases with different powers and different lifespans all swirling around up there. How in the world do scientists figure out what their combined real-time impact is on the planet's energy balance right now? For that, they use a concept called radiative forcing. Now, it sounds really complex, but the idea is actually just a direct measurement of how much something, like a specific gas, is tipping the Earth's energy scale. A positive forcing means more energy is being trapped than is escaping, and that, of course, leads to warming. And this chart is where we really see the big picture. Even though CO2 has the lowest GWP, just one, remember, the sheer overwhelming amount of it in our atmosphere makes it the single biggest driver of the warming we're experiencing today. Its total impact, its radiative forcing, completely dwarfs the others. Methane comes in a distant second, followed by all the other gases combined. So we've gone through the science, we've met the players, we've looked at the numbers. But let's bring it all back home. What does this actually mean? What are the real-world consequences of cranking up this natural greenhouse effect? Well, the impacts of this energy imbalance are huge and far-reaching. It's the engine that's driving up global temperatures. It's what's causing massive glaciers to melt and our sea levels to rise. We see it in shifting weather patterns, which lead to more frequent and more intense storms, droughts, and heat waves. And it's not just the air. The oceans are absorbing a ton of this extra CO2, which causes ocean acidification. That's a huge threat to marine life, from tiny plankton all the way up to our magnificent coral reefs. So when you really think about it, the specific mix of these gases in our atmosphere is literally writing the story of our planet's climate in real time. They set the stage for all life on Earth. And that leaves us with a pretty big question. It's not about what's already been written, but about what comes next. What will the next chapter be?